Hello students, in previous lecture we already discussed rotating molecule possesses different rotational energy levels having rotational constant J. In today's lecture we discuss expression for the wave number of lines. Expression for the wave number of lines in a rotational spectrum of a diatomic molecule. Expression for wave number of line in rotational spectrum of diatomic molecule. Then we already know that when rotating molecule absorb certain wavelength from microwave region, then it's that rotating speed of rotational changes. This is similar to gear system in a two-wheeler motorcycle. In first gear it rotates slowly. In second it rotates fast. In third it again fast. In fourth it rotate again fast. Similarly, in a rotational excitation means when molecule is at lower level, it absorbs certain wavelength, which is equivalent to energy gap between that two energy levels. And when it absorbs that light wavelength, its speed of rotational increases. That is nothing but rotational excitation in upward direction. While in lower downward direction, that molecule loses that equivalent wavelength, equivalent energy, which is equivalent to gap between that two levels, and its speed decreases. This is nothing but which results in rotational spectrum. That is that rotational spectrum consists different lines, and that lines are results because of that rotational excitation of molecule, and which is equivalent to that energy difference between that rotational levels in molecules. And that that rotational energy levels, that is property of molecule which is fixed, that are always quantized, and therefore from that gap, from that wavelength, that wave number of lines in spectrum, we judge that energy gap between that rotational energy levels, and from that gap we also judge which molecule is that which spectrum, that from that spectrum we judge the molecule associate with that spectrum. Then we start here this expression, that is expression for wave number of lines in a rotational spectrum of diatomic molecule. We know that for rotational energy calculation, there is a fixed equation in quantum mechanics. That equation, E rotational is equal to h square upon 8 pi square I into j plus 1. Consider here two rotational energy levels, E2 and E1. That for E2, consider that rotational energy of molecule J2 in bracket J2 plus 1 into h square upon 8 pi square I. While for E1 level, initial level, that one is considered as the energy level E1 equal to this. Then when molecule excited from E2 to E1, that is initial level consider E2, higher level, while final level consider as a E1, that is lower energy level. Then what will happen, that when higher energy state rotating molecule comes to lower energy state, speed decreases. That means it loses energy and it emits that equivalent wave, which is nothing but depends on that energy gap between that two rotational energy levels. Then that emitted energy will be delta E, which is nothing but energy in the initial state minus energy in final state, that is E2 minus E1. Substitute that two equations, that resultant equation we got h square upon 8 pi square I into J2 plus 1 minus J1 plus 1. By rearranging and solving that, we got equation as a delta E is equal to, in bracket, J2 plus J1 bracket complete plus 1 and into J2 minus J1 into h square upon 8 pi square I. Then we know that delta E is equal to H into mu. Delta E is H mu. Therefore, substitute that value, that H square will cancel because of H mu. If you substitute H at this side, that above H square will cancel that to that H. Then that equation becomes J2 plus J1 plus 1 into J2 minus J1 into H upon 8 pi square I. That is square cancel here, remember. Then we know that mu is equal to, if we consider that frequency in a form of wave number, mu bar, then that frequency is equal to C into mu bar. That is, mu is equal to C into mu bar. If you substitute that at this side, that C become at this side, then equation become J2 minus J1 in bracket J2 plus J1 plus 1 into H upon 8 pi square I into C. That H upon 8 pi square I into C, which consists all terms constant, therefore this considers as a new constant, which is nothing but rotational constant B0, which is also known as Bajram constant. Then our final equation become mu bar is equal to J2 minus J1 in bracket J2 plus J1 plus 1 into B0. By substituting that values of J1 and J2 for different energy levels, rotational energy levels, that J is rotational constant. If we substitute different value of J1 and J2 in this equation, then we can calculate that rotational energy changes, delta E. Then what is selection rule for rotational spectroscopy? Selection rule is delta J is plus minus 1. That is, molecule from second level, molecule jump in first level, or from first level, molecule can jump in second level only. It not directly jump in third level. Stepwise, is jump from first to second, second to third, third to fourth. That is, one step only allowed. Increase or decrease by one step is allowed in rotational spectroscopy. That is, delta J, change in that rotational energy level, is plus minus 1, downward or upward, one step change. Therefore, consider here J2 minus J1. That is, we consider here downward excitation of molecule by emitting energy. Therefore, J2 minus J1 is 1. That is, as like from second, 2 minus 1, that is 1, as like that. Then, therefore, J2 is equal to J1 plus 1. J2 is equal to J1 plus 1. Substitute these values, that is, J2 minus J1 is 1 and J2 is equal to J1 plus 1. Substitute these two values in above equation. Then that equation will become mu bar is equal to 2 in bracket J1 plus 1 into B0. Mu bar is equal to, that is wave number of that rotational line in rotational spectrum, will be mu bar, which is equal to 2 into J1 plus 1 into B0. By substituting values of J1, we here find out, calculate different that is value of different lines, the wave number of lines for different excitations. Different excitation. Consider first excitation from 0 to 1. Upward excitation consider here. From 0 to 1. Then what is J1? 0. And J2? 1. Substitute in that equation. We got mu1 bar, because that results in first excitation 0 to 1, first excitation. Therefore, first line in rotational spectrum of diatomic molecule. Therefore, mu1 bar is equal to 2b0. Then second line consider as a from first to second excitation, first level to second level. Then J1 become 1, J2 become 2. Then substitute that J1 then mu2 bar, because second, therefore mu2 bar is become 4b0. Then third excitation, that becomes 6b0. Then fourth, 8b0. Then 10b0. Then 12b0. Then 14b0. As like that. That means that if we consider this wave number of these different lines, then it is observed that there is constant gap between lines, two lines. That is, that constant gap is 2b0. 2b0. That is, here we conclusion from that this rotational wave number of lines is that lines are present in microwave region. All our lines are present in microwave region. That rotational energy gap between that levels results that wavelength, emission of wavelength, that wavelength from microwave region. Then the spectrum consists of equally spaced lines. Gap is always 2b0. Gap is 2b0. That is, the spacing between any two successive lines is constant and equal to 2b0. That is, and final conclusion is, at room temperature, rotational energy level, that is levels changes, rotational excitations up to J is equal to 5 are possible. That is from 1 to 2, 2 to 3, 1 to 2, 2 to 3, 3 to 4, 4 to 5, up to that levels excitations are possible, and which results in a rotational spectrum. This one is diagram for that excitations, and here below that that shown are rotational lines spectrum of molecule, which shows that energy 2b0, 4b0, 6b0 having constant energy gap. Then from here we stop. Now, by using this equation, that is energy gap 2b0, line gap is 2b0. By using this equation, we already know that b0 is equal to, which is constant, which is equal to h upon 8 pi square I into c. From this equation we calculate, which is very useful for calculation of internuclear distance. We discuss that in next lecture. Thank you.